and yellow. It's just those three colors that we're making. We're going to make a tree diagram to identify the sample space for the different ways that you can build this rainbow without repeating a color. So that means that once I use blue, I cannot use blue again. Once I use red, I cannot use red again. Okay? So the very first possibility, our very first choice of colors has all three available. We could have red, we could have blue, we could have yellow. By the time we get to our second option, if we chose red, we only have what left? Blue and yellow. If we chose blue, we only have what two options left? Red and yellow. And if we chose yellow, we only have red and blue. Okay? And then by the third option, because we have to choose all three colors, what's remaining for the first choice? Yellow. What's remaining for the second one? Blue. What's remaining for the third one? Yellow. What's for the fourth? Red. What's for the fifth one? Blue. What's for the last one? Red. Okay, so there's what our tree diagram is going to look like. Okay, based off of that, so I'm going to go ahead and write down what my sample space is. I should have 6 total outcomes that can be achieved for the order of my sample space. I have red, blue, yellow, red, yellow, blue, blue, red, yellow, blue, yellow, red, yellow, red, blue, yellow, blue, and red. Those are my possible outcomes that I've got. So we want the probability that the second color used is going to be red. That the second color that we use will wind up being a red. So what outcome numbers in my sample space will meet that criteria that the second color is going to be red? Paris? 3 and 5. Number 3 and number 5 have red as their second choice. Red as their second choice. So that means there are 2 of those out of 6, which simplifies to 1/3. That is 0.3 repeated, or approximately 33%. Okay, for the next couple of problems, problems 3 and 4, we're using compound probability to find the probabilities of flipping a coin and rolling a die. So we flipped a coin and we rolled the die. So I want the probability that the coin is going to land on heads. Guys, what's the probability that the coin will land on heads? 1/2. And then I want the probability that the die is going to land on an even number. How many even numbers are on a die? 3 out of how many total? 6. And then what do we do with those probabilities? Multiply them. So we're just going to multiply this together. We get 1/4 or 0.25 or 25%. Okay, you need to know all the ways to be able to write our probability because you don't know which way they're going to ask for it. All right, for problem number 4, we want the probability that the coin is going to land on tails and then a prime number for the die. So again, probability of tails is what? 1/2. Prime number. How many prime numbers are there on the die? 3. There are 3 prime numbers. Guys, write this off to the side. The smallest prime number out there is a 2, not a 1. 1 is not prime, 1 is not composite. In order for you to be a prime number, you have to be divisible by 1 and itself. So it means you have to have exactly 2 factors, 1 and itself. If it has more than 2 factors, then it is not a prime, it's a composite. The value 1 has only 1 factor, 1. Okay, the value of 1 is only divisible evenly by 1. So it has only a single factor. That makes it not a prime, nor is it a composite. Okay? kind of like how 0 is not positive and it's not negative. It's like one of those kind of mathematical oddities. So we have 2, 3, and 5. Those are our prime numbers on a die. 2, 3, and 5. So that means that we have a total of 3 prime numbers out of 6. We're going to multiply that, and again, we'll get 1/4, or 0.25, and 25%. Eob, did you have a question? Oh, okay. All right, problem number 5 has nothing to do with the coin or the die. It's its own little thing. We're going to roll a factor of 6 from a die, a factor of 6, and then we're going to pull a vowel from the alphabet. Okay, so factors of 6. So off to the side, I'm going to go ahead and write down factors of 6. Those are what times what will equal 6, okay? Factors of 6. So obviously 1 times 6 is going to equal 6, and 2 times 3 is going to equal 6. So how many factors do we have? 4. Factors of 6. Those are values that can go into 6. Okay? So we have 4 factors out of 6 total numbers on the die. And then to roll a vowel, or to pull a vowel out of all the letters in the alphabet. Pulling a vowel out of all the letters in the alphabet. How many vowels are there? 5. How many letters in the alphabet? 26. 26. Okay, so then we're going to go ahead and multiply that. What does that give us? 5 out of 39. 5 out of 39. Okay, and then if you wanted to convert it, you can do 5 divided by 39. You're going to get approximately, so we'll round it, 0.13, which is approximately 13%. Okay, you could put 0.128 or 12.8%. It's perfectly fine. Any questions? Okay, let's go ahead and move on to simulations. So for simulations, what a simulation is, it's just a way to model a probability experiment. So using real-world situations, how can you use these probability experiments to model those situations? Okay, so when you're trying to create a simulation, or when you're trying to identify what probability experiments could use, you should identify these 2 things. You need to know how many possible outcomes does this real-world situation have, and then how often is this real-world experiment or situation happening? Okay. No. Okay. Miss Croy's kids, one of you want to come on up and grab this? This is your instructions for today. Okay, so you want to know how many possible outcomes are there in this situation, and then how often is the situation occurring. So before we do that, the first thing that we want to identify is what kind of simple experiments do we know that have these following outcomes? So 2 outcomes. What experiment out there do we know that has 2 outcomes in probability, Veronica? Flipping a coin. Go ahead and write that down. You flip a coin. A coin has 2 possible outcomes. What other experiment do we know, and where would it belong on outcomes? What's another experiment that we know? Armando? A spinner, okay. And the spinner can have all sorts of different outcomes, can it? A spinner can have 3 outcomes, can have 4 outcomes, it can have 5 outcomes. So for these right here, I'm just going to go ahead and indicate that we would probably use a spinner. Whether it's a 3-section spinner, a 4-section spinner, a 5-section spinner. What about the 6 outcomes? What would we use for 6 outcomes? Kavya? A die, right? A number cube or a die. We would roll a die. It's got 6 outcomes. Okay, then we get up to higher outcomes, like 8 outcomes, 9 outcomes. So these start to become things, because you're not going to sit there and be like, oh, it's got 4 outcomes. I'm going to have a 24-section spinner. your spinner is going to be cut really, really, really tiny. It's going to be hard to see. So when you start getting up into these bigger outcomes, you start doing combinations of different experiments. So maybe I could flip a coin and spin a 4-section spinner. Flipping a coin and a 4-section spinner. Or I could flip 3 coins. I could flip 3 coins and that would have 8 outcomes, right? Heads, heads, heads is an outcome. Heads, heads, tails is an outcome. Heads, tails, heads is an outcome. Heads, tails, tails is an outcome. You've got all these different outcomes that could represent 8. Maya Isabel? A clothing combination? So we're thinking more along things that are physical, like the stuff that we've talked about, like pulling a marble out of the bag, spinning a spinner, rolling the die, flipping the coin. Not necessarily going in your closet. Your closet is actually a real world situation, right? Those are real world examples. When we're talking about the probability experiments, we're talking about the simple, basic events of chance, okay? So I'm going to write down just a couple of examples that you could do here. You could flip 2 coins, flip 3 coins. Or you could flip a coin and spin a 4-section spinner. Okay? Or maybe you even have a bag of 8 marbles. I mean, those are just different things. 9 outcomes. 9 outcomes, you could do 2 3-section spinners. You could have a spinner, or you could spin 2 3-section spinners, because 3 times 3 is 9. So maybe one of the spinners is labeled A, B, C. The other spinner is labeled 1, 2, 3. Okay, so you could have A1, A2, A3. You could have B1, B2, B3. C1, C2, C3. Yes? Okay, so let me go ahead and model that for you on a blank sheet of paper. So Ray asked, she said she was confused. How does 3 coins have 8 outcomes? So look at your tree diagrams. The first possibility of a coin would be heads and tails. Now when I go to my second coin could land on heads or tails. Heads or tails. And then my third coin could land on heads or tails. Heads or tails. Heads or tails. Heads or tails. Okay, so what we are seeing created here is the very first one is all 3 are heads. Your second possible outcome would be the first 2 are heads and the last one is tails. Then you have heads, tails, and heads. Or heads, heads, tails, and tails. Okay, then you've got tails, heads, heads, tails, heads, tails. And then tails, tails, heads, and tails, tails, tails. Okay, so you have all of those different possible outcomes that you could achieve from 3 coins. Okay? All right, so let's take a look here. You decided to treat yourself to a night out. You can either go to the movies or you can go out to eat. You're going to create a simulation that would model the situation. So like I said before, you need to identify how many possible outcomes does the situation have, and then you need to identify how many times is the event happening. Okay? So how many possible outcomes, how many different choices do we have here, guys? 2. We have 2 different choices. We could go out to the movies, we can go to the movies, or we can go out to eat. That's 2 choices. We have 2 outcomes. How many times are we doing this? Just once. We're going to just do this one time. So 1 time represents the trial. How often we're doing that is going to represent a trial. So in this case, what we would do is we would say we are going to flip a coin, because a coin has 2 outcomes. You're going to flip a coin 1 time. You're going to flip a coin 1 time. All right, taking a look at problem number 2. At your favorite ice cream shop, they have 4 different flavors. On a Friday night, they served 200 customers. We want to create a simulation that would model the selection of the ice cream by the customers. How many different options do we have? 4. We have 4 different options. 4 different flavors are the 4 outcomes. What did we say we would use for 4 outcomes? A spinner. A spinner is a really good choice. A spinner is a really good choice. Of course, we have to identify that it's a 4-section spinner when we indicate what our model is going to be. How many times are they selecting ice cream? 200, right? You have 200 customers. That is going to represent 200 trials. So 200 customers is going to represent 200 trials. Okay, so we're going to spin a 4-section spinner 200 times. We're going to spin a 4-section spinner 200 times. Okay, a woman is pregnant with triplets. What's triplets mean? 3 babies. She's pregnant with 3 babies. So we want to simulate how each gender could be chosen for each of the children. How can a gender be chosen for each child? So how many outcomes do we have, guys? 2, right? When they are identifying what the gender is for the child, it's either going to be male or female. Okay, how many trials? 3. You've got 3 babies. That's 3 selections of a gender. Okay, so you have 2 genders. So that means you have what simulation? A coin. A coin's going to have the 2 simulations or the 2 outcomes. 2 genders, 2 outcomes. That's a coin. And then we said that there are 3 babies. So that's going to be 3 trials. So you would flip a coin 3 times. You're going to flip a coin 3 times. Okay, these are some really basic, straightforward ones. On the next page, we've got 4 situations, 4 scenarios, and 4 simulations that you can choose from. You're going to match. You're going to match. So what I want you to do is I want you to take out a pink, a blue, a green, and an orange highlighter. You're going to highlight, you're going to highlight the first situation in pink, and then you're going to find the simulation that matches with that situation, and you're going to highlight that simulation in pink. Now, if you are unsure about whether the simulation is what it is, you could just put a dot. Like, oh, maybe I think it's this one, so I'm going to put a little dot right by it in pink. I don't want to highlight it yet just in case I'm wrong. Do you see what I'm saying? So highlight the situation. So we're going to do pink for the first one. We're going to do blue for the second one. And I do apologize. I forgot that we can only print in black and white. I had originally had them all colored in pink, blue, and then green and orange. So the third one is green. And then the fourth one is your orange. And then right next to the simulation that you think it belongs to, you're just going to put a colored dot. Because if you are wrong, you don't want to highlight the whole thing in that color. So take the next 2 or 3 minutes and see if you can match the situation with the simulation here. Okay, let's go ahead and go over these. So for problem number 1, it says a small lake. There are 25% of the fish that are female. In a small lake, 25% of the fish in that lake are female. You're going to capture a fish, record whether it's male or female, and then toss it back into the lake. If you repeat the process 5 times, what is the probability that at least 3 of the 5 fish are female? Which simulation would model that? Number 1, 2, 3, or 4? Number 2. Okay, number 2 is going to model that. If you make a spinner with 4 equal sections, makes sense because 25% is 1/4. You're going to label it 1, 2, 3, 4. You're going to spin the spinner 5 times. Okay, yeah, you're going to pull a fish 5 times. And then you want to identify how often does a 4 appear 3 or more times in your probability. Okay, so, and that makes sense. You want at least 3 of the 5 fish to be female. So this is going to be your matchup. This is the simulation that matches it. So we cannot use number 2 anymore. Okay, let's take a look at problem 2. Elena makes 80% of her free throws. 80% of her free throws. Based on her past successes with free throws, what is the probability that she'll make exactly 4 out of 5 free throws in her next basketball game? 80% of her free throws are made. We want the probability that she's going to make exactly 4 out of 5 in her next game. Is that going to be simulation 1, 3, or 4? 4. Simulation 4. She places 8 blue chips and 2 red chips. That's 10 chips. 8 out of 10 is 80%. 8 out of 10 is 80%. She's going to shake up the bag, pull out a color, record it, and put it back in the bag. She's going to repeat the process 4 more times to obtain the simulated outcome. Then she's going to keep repeating it over and over and over again, and then document exactly how many times did she get 4 blues out of the 5 choices. Okay, so that simulates what she's wanting. There is your matchup. Okay, problem 3. On a game show, a contestant must pick one of 3 doors. In the first round, the winning door has a vacation. In the second round, the winning door has a car. What's the probability of winning a vacation and a car? Which one is it, 1 or 3? 1. Outcome or simulation number 1. You toss a fair or standard number cube 2 times and record the outcomes. So yes, I know the number cube has 6 outcomes on it, right? But they want to land on a 1 or a 2. So that means they have 2 choices out of 6 that can land on. That narrows you down to 3 actual outcomes, okay? So that's going to simulate the 1 out of 3 there. 2 out of 6 is the same thing as 1 out of 3. All right. So that means that the last one is going to be outcome number 3. Your choir is singing 4 concerts, and you and one of your classmates both learn the solo. Before each concert, there's an equal chance the choir director will select you or the other student to sing the solo. We want the probability that you will be selected to sing the solo exactly 3 of the 4 concerts. That's going to be simulation number 3. You toss a fair coin 4 times and record the outcomes. You repeat the process many times and find out exactly how often did you land on 3 heads out of the 4 coins. You got 3 heads exactly. 3 heads and 1 tail exactly. Okay, so that would be the 3 out of 4 choices. Okay? All right. You've got 12 minutes to be able to get into your quizzes. It's 10 questions. You get 2 tries. 2 tries only